So, hello everyone. Great that you have me here. I would like to speak about using artificial intelligence in manufacturing. I have brought with me a lot of use cases, and good to know that Porsche is afterwards speaking, because I also have a use case with Porsche, realized a while ago. Very briefly, if you don't know, just a second. If you don't know, Fraunhofer, especially Fraunhofer IPA, which is the Institute for Manufacturing Engineering and Automation here in Stuttgart. We are located in Vaihingen, where also the university is. We are doing a lot of automation technology, like robots, but of course using AI to support German companies for applying artificial intelligence in their manufacturing processes. For those of you who might not familiar what actually production or manufacturing is, very briefly, in a nutshell, how a manufacturing process looks like on a very abstract level. You have some machine, and this machine you need to feed in some input, which is material, energy, information, and then this machine is transforming this input into an output, which might be a final product, which you can sell, or what is called a half product, which is then processed further by another manufacturing process. That's very briefly how a manufacturing process works. And of course in Germany, which is a country with a lot of manufacturing industry still, hopefully also in the future, of course you have to think about how AI could help. And I brought you some numbers with me. I looked it up from several studies which are highlighting the gains you can get by using AI in manufacturing. For instance, a very common use case is using it for quality control, so like visual inspection with cameras, and the images are then processed by machine learning. You can expect quality gain by up to 30%. Or using optimization, AI-based optimization for process optimization, you get an increase of the productivity by maybe 20%. And maybe the golden boy of AI in manufacturing is called predictive maintenance, where you try to predict if parts of your machine will break down in the near future. Because you know this in advance, you can take actions like ordering material, plan in the working stuff, and avoid an unplanned downtime. But actually, this is one of the hardest use cases in manufacturing by my experience. There are others like quality control that can be done much easier. So in the following, I would like to give you some insights of a project we have done in the recent years with several companies in Stuttgart and around. And to give this thing a bit of a structure, I brought with me a abstract manufacturing process, a multiple stage manufacturing process from inspection of incoming goods over the actual manufacturing parts, then maybe end-of-line inspection and shipping out the product to the customer. And along this line, of course, you can imagine tons of AI use cases. But because we have limited time, I only brought 5 use cases with me. And let's start with the first one, the order planning. So the customer wants to order something and the company has to decide when to process this order. And this is actually the Porsche use case I already promised earlier. So Porsche, I guess everybody knows who and what Porsche is. Of course, it's also doing, as any car company, doing an order planning. So to decide when to plan in a customer order to produce the Porsche. And especially in the specific case of Porsche, very important is if the customer has a specific desire when to get the car. For instance, he would like or she would like to have the Porsche at the 5th of May. It should, of course, be ready at the 5th of May, not the 6th of May, and not on the 4th of May. Because 5th of May, they want to go to holidays. I don't know. And this promise was becoming more and more demanding to fulfill because Porsche became larger over the last 10 to 20 years. And their pure mathematical optimization-based order planning algorithm had issues with this increase of Porsche. So they asked us, maybe AI could help here. What we came up is this 3-stage process you see here. And the most important part is the first one, which is called configuration generator. I usually call it the AI-based glass ball, because we would like to anticipate customer wishes before the customer actually know which kind of wishes they do have. And therefore, we process historic customer orders, but also data from the car internet configurator. Every car manufacturer has this kind of a configurator where people design their car and never order it because of lack of money, or I don't know. And but this is an important tool because you get future trends like orange is the new black or something like this. And based on that, we generate what is called a plant order. This is a quite old concept in manufacturing. A plant order is not an actual customer order. It's more like a virtual order. But it is really representing a fully specified car. It could be produced if someone is ordering it. And therefore, we use reinforcement learning, a specific breed of machine learning, to generate these kind of plant orders out of the vast amount of data we have got. With these plant orders, we go to the second stage and completely plan what is called the order book. So you could imagine you have a calendar month and you planning the completely month with cars. And this is where optimization comes in to decide which car needs to produce when under certain constraints you have to fulfill. You cannot produce any car at any time because you have certain constraints. Because, for instance, if you would like to install a glass roof in a car, it takes more time than a normal roof, and you can only produce maybe 20 glass roofs per day. These kind of constraints need to be considered. Because we have now completely planned order book, we can do, for instance, scenario planning, which was not possible before. Scenario planning could mean, for instance, how does the fleet needs to look like if we have to minimize CO2 consumption? Or how does the fleet has to look like if you want to maximize the profit? Something like this. Or everybody knows of the Ukraine war, but maybe most people do not know, 80% of all the cables in a car is coming from the Ukraine. Once the war started, you had a shortage, of course, of this cable. So what does this mean for my production if this kind of shortage happens? This can be planned in. And the last step is then we play Tinder for Porsche. So we are looking, a customer is coming, has a wish, which kind of car he would like to order. And now we are looking for the best match in the order book. So the best car satisfying the desires, the configuration of the customer. Just to give you an impression, a Porsche can have up to 4.5 billion different ways how it could be configured. So the probability that we get the perfect match is zero, like in real life, you know. And therefore, we look for the best match, which is not a 100% match, and reconfigure it and optimize again. And we have done this together with a PhD student to get some scientific rounding, so to say. And we were able to show by this kind of process, we could optimize two conflicting goals. We can make the production more stable and more flexible. Usually you have to compromise the one against the other. We could optimize both simultaneously. Second example is parameter optimization in manufacturing. Every production machine has parameters, like the hyperparameters in machine learning algorithms. It's actually quite the same and use the same technologies actually. So you need to twist these parameters, and if you do it good, you get maybe a stable process with high quality. So we have the process parameters. They somehow impact the product quality, which can we either measure or estimate from other sources. And then we compare the product quality with, of course, the target quality. And if there's a significant deviation, we have to adjust the parameters. If we do it right, we get a high throughput, high quality production, but usually this parameter optimization is done manually by experts. Maybe they know the machine since 20 years and they know which kind of knobs needs to be adjusted to get a stable, high quality process. But as you all know, we are facing a demographic problem. These people are getting out of the job market due to age, and we do not have the same amount of people coming into the job market. So we have to think about how to automate this process, and of course AI could be of help. So the idea is to put AI in this parameter adaptation box on the right. We did this several times already. One example we did is with Trumpf. TRUMPF is also located near Stuttgart in Ditzingen, well known for the laser cutting machines, for instance, cutting steel plates. And in this case, it's actually about this process. So imagine you have a large sheet of metal, and out of there you need to cut out smaller pieces. And the most important quality aspect is the cutting edge. The better the cutting edge, the less after work you have to be done. The problem is the quality assessment of this cutting edge is usually done also manually. So an expert is looking at the edge, maybe using the fingernail and saying, oh, it's a bit rough. We have to adjust the parameters to get a smooth and nice cutting edge. So the idea was how to automate. And the first thing is we need to quantify the quality, not have a qualitative assessment by a human. It needs to be automated, the quality assessment. Therefore, we used camera to make images from the cutting edge and process this with a deep neural network. It was the first time done ever. So we solved this problem. We were able now to estimate several quality parameters like the burr height or the roughness of the cutting edge. Second, another AI model is now using these quality estimates to provide parameters to the human worker, and the human worker can now decide whether she or he adapts these parameters or just ignores them. So that was the second step, and we did then a lot of experiments, so man against machine, so to say, and to see if our idea works out. It was working out nicely. So for instance, what we got out of these experiments, that the human expert usually has adjust 5 to 7 parameters, more is usually overwhelming. An AI, of course, has no limitation on the number of parameters it can adjust. This parameter adjustment is an iterative process. You do a cut, quality assessment, parameter adaptation, another cut, quality assessment, rinse and repeat. Yeah? The human worker needs 15 to 20 of iteration steps. The AI needs 3 to 5. And once the AI is finished, the product is not only of higher quality, the entire production process is faster. So you get more out in shorter time. And here you can see the evolvement of such a cutting edge. Here you have bad quality, high burr height, for instance, and after 5 to 6 adjustments, you get an almost perfect cutting edge. This was so nice that TRUMPF made a product out of that. So we went from research to POC to a final product, all AI-based. So every customer who is now ordering a cutting machine from TRUMPF can now order, in addition, this what is called the cutting assistant. Second example for parameter adaptation is in car manufacturing. So what you see here is a typical situation in the body shop where you have metal sheets which are connected together by spot welding. So if you can go to a body shop of any car manufacturer, there are almost no humans anymore. There are a lot of robots, and this is the most common process a robot is doing in the body shop. And what you see on this, maybe I'll repeat the video, when you see a lot of sparks flowing around. So maybe they are celebrating New Year Eves. Actually, if you see sparks, you have an issue. This is a quality problem. A spark means molten metal is spreading around and maybe flowing somewhere, maybe on the top surface where you later on have a finishing. And you then have a quality issue because you have some kind of, how to say, pickle in German, a pimple. So you need to avoid that. So how to do? Of course, we can use again AI for this purpose. Therefore, we used data which is already generated out of the welding process. This is high frequency time series data, like voltage or current data. In addition, we also used ultrasonic inspection, which is the common way how the quality of a spot weld is assessed. You have an ultrasonic camera, which is held by a human worker to the spot weld, and then the quality is assessed. This is the ground truth, so to say. And you only have very limited ground truth because it's a time-consuming process. But it provides us the labels we need to have for the machine learning training. So we use this information to train a deep neural network for this purpose, and then we can do quality prediction for each individual spot weld. This is important information. In a common body shop, less than 1% of the spot welds are actually quality controlled. So the vast majority goes out without any quality inspection because of the time it takes to make a quality inspection. We can now do 100% quality inspection with this solution. But not only this, we can also now target the quality engineer because the model makes a prediction. And if the model indicates there might be an issue with a spot weld, we call it a suspect spot weld, the quality engineer can now be targeted to this one specific spot weld and make an ultrasonic inspection to check whether it's true or not. But of course, this model can also be used then to do parameter adaptation very similarly as I have shown with Trumpf. So that in an ideal world, we have no quality issues at all anymore. We are not yet there, but it looks not that bad. We did this, for instance, with Audi. So these are some numbers of the first test we did. So we were able to show, just by installing it to 3 to 4 robots, and usually they have hundreds of robots, we could already save 30% of the manual inspection work. We did this also with BMW in the USA. There it was 50%. Next example is robot automation. I brought no humanoid robot, even though this is maybe the most hyped topic currently besides Gen AI and agentic AI. This is a very common robotic process in manufacturing. It's called bin picking. So you have a bin which is having a lot of chaotically stored items like these metal beams. And oftentimes these metal beams are removed by a human worker, and you can imagine if this person is doing it one day long, this person is moving tons of material per day. And over months and years, this causes wear in the human body. So therefore, you try to use a robot for this purpose. But for the robot to solve this problem, you need to estimate the pose, so the orientation of the individual items, in order to decide which one needs to be picked in such a way that the grasp is robust. So when moving around, this gets lost into the machine and maybe blocks the machine. So we are speaking about industrial process. It needs to be as perfect as possible. It's not like a shaky human robot moving things around. It needs to be robust. Therefore, we can train, of course, the machine learning model to do this 3D pose estimation. Problem is, getting 3D data out of manufacturing process is very expensive. It takes a lot of time. The labeling effort is immense. So making human labeling is not the way to go here. So what we did instead is we assembled a physics-based simulation where we can generate simulated data, which is dropping items physically correct into virtual bins, and use this data for training a deep neural network for the pose estimation. This works pretty fine. If you would like to come to Fraunhofer in Vaihingen, you can see this kind of demonstration cell. This is an UR robot that is moving around, in this case U-bolts, U-shaped bolts. Now also can directly see the simulation environment in a second. Now, this is how the simulation looks like. This flickering is actually the simulation of the 3D sensor. So we can generate in short time an arbitrary amount of bin picking situation. This is also a tough problem. Some items intertangle each other. And usually you only want to grasp one item after another. So you need to detect this kind of situation and resolve them. And this was in the past a very tricky problem. Oftentimes it could not be solved. But again, by using reinforcement learning, we were able to train strategies how to resolve these kind of entanglements directly in the container. As showed, like lifting it up and then letting it drop, this is just a show. If you have a sensitive surface, dropping a metal item on a surface can destruct it. So you really need to resolve it in the container. We improved this over the last couple of months to make it really fast. So here you can see our fastest version. This robot can make this kind of picks in 1,300 picks an hour. This is faster than a human can do. A human can be fast, but not for 1 hour. And also what we did, we developed another algorithm which is stowing the items in an optimal way so that we can minimize the usage of the space. This is called the nesting. And nesting, I would like to look a bit more deeper because it's a quite interesting problem. You find it in many industries, like garment industry, metal sheet cutting, like with Trumpf, this warehouse situation where you have to store stuff in a container. Here we would like to consider Trumpf again. So you have this huge metal sheet. Imagine this is 3 by 3 meters, 4 by 2 meters, so really large. And out of this large metal sheet, you have to cut out smaller pieces, like here. And they can be arbitrary in shape. If this would be like rectangles, like in the, I don't know, in the wood industry, this is an easy problem, solved since centuries, tens of years maybe. But if you have no assumption about the shape, this is really a complicated problem. Just to give you an impression, if you want to nest 100 parts on here, you have 10 to the power of 158 combinations. To give you an impression how big this number is, the known universe has around 10 to the power 80 atoms. So the exponent is just factor 2 less, but this is important. This means 1 to the power 160 means each atom has a universe of atoms. This is how big the solution space is. There's no chance to find the optimal solution, not at all. It's by far more complicated than playing Go, for instance. But if you find a good solution, and we maybe just save some space, some scrap here, you can save a lot of CO2 that is wasted otherwise. This nesting problem can be then subdivided in 4 sub-problems. For instance, the first one, you have to select which kind of sheet is used. If they all have the same size, this is not a problem at all. Second, you have to assign parts to sheets. Third, you have to sequence the sheets because all the nesting algorithms expect to have an order and they nest one after another. And the last one is the actual nesting. And for the next couple of minutes, I would like to focus on the second and the fourth problem, so the sequencing and the nesting itself. So sequencing, assigning. Consider following toy example. The light blue area is our metal sheet, and we have already nested 2 parts on it. The dark blue square and the green triangle. So we have some space left, and if you calculate the area of this space, this is large enough that it can host 2 triangles, 2 circles, or a mixture of both. Because both the triangles and the circle have the same area, also the shape is different, so we could nest 2 of them. If you nest a triangle, the following situation happens. You can only nest 1 of them, even though the space, the free space, would be enough to nest another one, or a circle. If you do the same with the circle, you have no issue at all. So the question is, what happens here? Why can we do circles but not triangles? And of course, it seems not to have only to be a matter of area. Also the geometric compatibility, so the shape of the items and their correlation under each other has very big impact. This is called geometric compatibility or something like this. And we found a measure to calculate this relation between the parts, which is called the GCI, the Geometrical Compatibility Index. And actually the nice thing about this index is, whether it's nice, let's decide, it has no formula. You cannot write it down and calculate it by hand. It can only be calculated by using a machine learning algorithm. It's quite complicated. But by using this measure, we're able already to save computation time for nesting, and of course, more importantly, we can save a lot of waste. We have not yet placed any item on the metal sheet. This is where the subprogram 4 comes in, the actual nesting. We developed another algorithm, which is again based on reinforcement learning. And we compared it with a well-known heuristic in this field. It's called DeepNestPert. It's a deep learning-based nesting algorithm. And we compared it here in several very complicated nesting situations, where you also can have nestings of nestings, so nesting squared, where you fit in the holes of one part other parts, and another one in the parts of the nested part. And when you compare, for instance, this one against this one, our solution has left a lot of free space where you could nest additional items. This space is not available here. And if you do then the calculations, our solution is 97% faster. Deepness port needs hours. Ours only needs a couple of seconds for nesting it, because it's just an inference process in a deep neural network. We use significantly less waste, and we make no errors. Deepness ports, for some reason, sometimes finds nesting which are physically just not possible. Last one, you might wonder, I have not yet used the word large language model and agentic system, because all this problem I've shown you are classical, in quotes, machine learning algorithms. But of course, GenAI has also its use in manufacturing, very unlikely on the shop floor, but on other parts. For instance, using it for programming machines. In manufacturing, you have oftentimes very odd languages like SPS programming, stuff like that. And here we have a scarcity in human sources. Virtual field assistants, where you would like to speak with your machine as you would like speak with your coworker. Logbook analytics, making sense out of the data that is provided by the machine. And data synthetic, so generating synthetic data for instance, quality control. I would like to look in two of the four examples. The first one is the virtual field assistant. We built this for a company. Unfortunately, I cannot reveal the name, which is some kind of a manufacturing chatbot, or a maintenance chatbot. So the machine has some issue, oftentimes providing what is called an error code. And behind this error code, usually look into a big manual, a lot of paper, and then, that's the issue and how to resolve. Now, of course, with a chatbot and with a reg system in the background, where all this digital paper is stored, the person can just look up the error code. The model is then providing an indication of the root cause and also, of course, how to resolve this problem. That's quite obvious how to make this. The second example is about quality control. Camera-based quality control, which is called automatic optical inspection. So you use a camera to assess the quality of the produced item. Usually these kind of systems should be fast because you have a high rapid production. So it's not slow down your manufacturing process. It should be effective. If there's a defect, it should be detected. And the other way around, if there's no defect, it should not create a false alarm. It should be robust. So if the environment is changing, or you have a high variance in your product, which is very common nowadays, it should still work, and it should be, of course, easy to use. We have just one problem in manufacturing. We have an unbalanced data issue, because in a well-running manufacturing environment, you have a lot of good data, but very little defects. So we have a highly unbalanced machine learning problem. Then, of course, you could ask the producer just for me that I can train a machine learning model produce defective parts. It will immediately show where the door is so that I can leave. So the alternative is, of course, to somehow make up the data. For instance, by using GenAI, models like GANs or diffusion models, because now we have the quality of these models that it actually works to generate synthetic defect images. Here I brought you some examples. This is from the textile industry, and this is, of course, the food industry. We have everywhere holes. Now you can guess which of the four images are real images and which one are fake images. And if you have an idea, just shout it out. That's tricky, I know. One person so far has resolved it, yeah? Sorry? Top right. Top right. So from your side, so this one? Not bad. The bottom one as well. So the two rights are synthetic and the left ones are real images. We developed a method which is called defect transfer GAN. That's a GAN model, a generative adversarial network. I guess you know roughly how this works. This model learns the style of specific defects like holes, cracks, scratches, and stuff like that, and transfers these defects from one image to another image, maybe also on an image where so far there was no defect. For instance, we have 4 materials: metal, woven material, leather, wood, and we would like to have scratches on these images because we are looking for scratches in our manufacturing process. You find a lot of state-of-the-art image generation models, but if you give them this task, they just do not work because they have issue with the little data we have available. So they maybe change the background, or they do not generate scratches at all, or they have some kind of odd artifacts. So none of these images are really useful, but with our model, it does not modify the background and it generates actually the scratch, like here, 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 or there. And we made experiments if these images are really useful for a downstream quality control machine learning model. And we were able to show that we can improve the quality control, so the accuracy of the model, by another 20% percentage points. The only issue is we have no control where the scrap will be at the end. The model decides. And if we want to have to control, we have to condition it somehow. And one way is to do it with segmentation maps. So what you can see here is a defect-free image of a welding seam. This is like a paint program, where with colors we can indicate where we would like to have some defects, like welding spatters. And then the model is generating in real time a defective image. You can see everywhere I do this golden spots, we do have a welding spatter. And now I change the color to pink. Pink is a porosity issue in our welding seams, and then the model adapts accordingly. We helped 1 or 2 companies with these problems over the last couple of years, from small scale companies up to the very big ones like Bosch or Siemens and similar. And maybe the last 1 or 2 minutes, I would like to give you some outlook what becomes more and more important in AI, specifically in manufacturing. So we've already spoken about synthetic data, how this is useful, time series analysis. Simulation become more and more important. Simulation processes in manufacturing are very daunting, very time consuming. There are now models, transformer models, which can speed up the simulation significantly. A very big problem is transfer learning. You can easily train a machine learning model for a specific issue, for a specific machine. And if you copy paste it to another machine, it breaks completely down. The process, these are physical processes. It's not that easy to copy paste machine learning model from one model to another one. And maybe one of the very big trends in manufacturing and AI is embodiment of AI. Like a humanoid robot, where AI is a key component of the machine, and you get capabilities which are not possible without AI. And this is very in line how, for instance, Yann LeCun, I guess everybody knows him, sees this. He was earlier this year in a conference, I think it was in Singapore, where he said, we need AI systems that understand the physical world. And this is where manufacturing is. We have forces, we have temperature. It's not a virtual process. Therefore, we need a different breed of machine learning AI models. And with this, I would like to close my presentation. Thank you.